This concludes the discussion about the Shannon theorem, and now we go to discuss another aspect of sampling and reconstruction, that is actually the whole devices that we are using in this course. So the whole devices, we have said, that are actually approximation of an ideal filter. The ideal filter cannot be realized, as I just explained, so for this reason we use approximations. What are the approximations? How these approximations are obtained? Basically, an whole device is based on the idea of the Taylor series expansion. So if we consider the signal x of t and we expand the signal around the sampling time k capital T, then we obtain this Taylor expansion. Now, obviously, what we have is that we don't actually have this derivative because we are in the discrete time domain, and so this derivative has to be approximated. So this derivative actually is approximated at the time t equal to k times t as the difference of the value at this instant of time minus the value of the previous sampling time divided the sampling time. So this is an approximation, a discrete approximation of this derivative. So we obtain this Taylor expansion with this approximation, and the idea of the whole device is basically to use part of this series to approximate the signal x of t. In particular, the zero order hold is obtained when only this first value, xk of t, is considered. The first order hold is obtained when both this first value and this second value is maintained, and then so on. The second order hold is when the second derivative is considered, the third order hold is when also the third derivative is considered, and so on. So you see that the name first order hold, zero order hold, is based on the order of the derivative that is included in this Taylor expansion. Obviously, this is an approximation. It's a very coarse approximation if we are approximating x of t just with the first value. And even when we consider, for instance, the first order hold, this is a better approximation, but we also to consider that there is an approximation that is caused by the fact that the derivative is not an exact derivative, but is a discrete time approximation of the derivative. So the whole device read the element of the sequence xk of t and produce an approximated, a reconstructed signal xr of t. So xr of t, in the case of the zero order hold, is just x of kt. In the case of the first order hold, then is the sum of these two terms, and so on. Okay? The whole devices interface discrete time system and continuous time systems, and as just shown, this can be represented with a transfer function when we assume that the sequence is generated by impulses. Now we consider two hold in particular, the zero order hold and the first order hold. So these are the two most simple hold devices that we can see. And in particular, most of the time, we will use the zero order hold in this course. This is the simplest possible hold. We also show that the first order hold, while in some sense improves the reconstruction of the signal, is actually bad for this course. This course is about control of discrete time systems, and so we are particularly worried about properties like stability of the system. And what happens is that a high order hold actually creates instability in the system. So it makes the system more difficult to control. And we show now these properties. So let's start now to talk about the zero order hold. And the zero order hold is, as we have shown, is represented by this transfer function. And this transfer function corresponds actually to the Laplace transform of this impulse response. And this is the realization of the zero order hold. So a device that is zero everywhere, apart in the time between 0 and the first sampling time, where is equal to 1. So talking about the zero order hold, let's start to look at this transfer function and trying to see the properties of this transfer function. The first question that we may ask ourselves is this transfer function introducing a pole in 0? Because you see that here we have a transfer function that has a pole in 0. And we know that a pole in 0 may introduce instability in our system. So is real that this transfer function has a pole in 0? That's actually not the case, because if we look at the expansion of this transfer function in 0, we see that that pole disappears. So x0 of s, we said that is equal to 1 minus e power minus s capital T divided s. Okay, so if we expand this around 0, so when s goes to 0, then h0 of s is equal to 1 minus 1 plus, so minus s capital T plus big O of f square t square, all divided s. So this is the Taylor expansion of this term, where big O of s square as t square means that these are all the terms that are of order at least s square. So this is actually equal, so this term and this term simplify, so it's equal to capital T, so this term, plus big O of s square t square divided s. Now we see that if s goes to 0, since this term has degree at least 2, this term is actually going to 0. And we see then that when s is very small, this old behaves as just a constant equal to capital T. Okay? So this shows that actually there is not, this device does not have a pole in 0. Let's analyze more properties of the zero-order hold. So in particular now we write the frequency response of the zero-order hold. So we replace S with j omega and see what happens. So when we replace S with j omega, we obtain this expression. And this expression can be manipulated to obtain this other expression. So let's look at the board how to get this expression with the sign. So we have the function written with the exponential. To write the sinusoid, we factorize e power minus j omega t over 2, and this is what remains. So you see that if you multiply this by this, you get 1, and if you multiply this term by this term, you get this exponential over here. Now we recognize that this is almost a sign, so we have to divide by 2 and multiply by 2 over here. Okay? So this can be written as sine of omega t over 2 divided, and there we have omega, and then here we have 2 omega, and then here we have e power minus j omega t over 2, and then we have that times 2 over there. So here we have times 2. Now what I want to write is also, I would like to write the same argument that appears here. Okay. So to do so, let's put a t over 2 over here and a t over 2 over here. This simplifies with this. And so actually what we obtain is the expression that we have on the slide. I want to point out also that the fact that this term appears over here is good. Because if we look at your slide some slides ago, we have found this relation. So the starred Laplace transform is equal to this expression where there is this 1 over capital T that we said let's forget for now. So this 1 over capital T does not play any role, because when we interconnect x star with the h0 of s, that 1 over t will be cancelled out by this capital T. So it's good that there is that capital T over there. So let's go back to our slide. And now what we want to do is to represent this function to see how this function behaves. So this is a complex function, so we have to represent the modulus or absolute value and the phase of this function. In other words, we want to represent the body plot of this function. So first of all, we want to compute the modulus, so the absolute value. So this is quite straightforward. We want to compute the absolute value of h0 of j omega, so the absolute value of this function. So we note that this, this term, this part here, is actually a real number, okay, while this term over here is a complex exponential. So this, in other words, is something that is of the type a e power minus jb. So we see that actually the absolute value of this term is modulus of a, okay? Because the absolute value of the exponential is 1. So this means that the absolute value of this is just the absolute value of this term. Capital T is a positive number, so we just write it outside, and so we get the expression that we have on the slide. The second part is to compute the phase of H0 of j omega. So to do so, we remember that when we compute the phase of the product of functions, then that's the sum, becomes the sum of the phases. So we are using the property that if we have a function f of omega times g of omega, and we want to compute the phase of this is actually equal to the phase of f of omega plus the phase of g of omega, okay? So if we want to compute the phase of that function, so the phase of h0 of j omega is equal to the phase of t plus the phase of sine of omega t over 2 minus the phase of omega t over 2 plus the phase of e power minus j omega capital T. Now, what is the phase of a real number? So if we plot this on the complex plane, a real number is a number that appears on this side, on this line, okay? So you see that actually the phase is 0, okay? The angle is 0. So the phase of this is 0, okay? This also is a real number, so the phase of this is 0. This is a complex exponential, so the phase of a complex exponential is the argument of that exponential. So the phase of this term is actually minus omega capital T. That is, yeah, in all this slide, actually this should be T over, on all this board, this should be T over 2, okay? So I forgot T over 2 over there, and I forgot T over 2 over here, so here this is T over 2, okay? So this is the phase. And then we have the phase of this function, okay? So what is the phase of sine of omega t over 2? So let's try to explain this. So sine of omega t over 2, well, the sinusoid is a function that does something like this, okay? But this is a real function. So if we plot this on the complex plane, okay, the sinusoid is a function that oscillates between +1 and -1. So here we have +1, here we have -1, and what the sinusoid does is that it oscillates along this segment here. Okay, so it goes up and down, left and right on that line. What is the phase of this? Well, every time that this is on this side, the phase is 0, and every time that this is on this side, the phase is minus pi, okay? So the phase of this term is sometimes 0, sometimes minus pi, or actually plus pi. You can write it as plus minus pi, because it depends, you can write it as you want. So this means that depending on the value of omega, this can be or 0, or it can be plus or minus pi. So let's look now at the slide and the representation of these two functions. So we see the absolute value is represented here, and is this basically a sinc function, so a function that has this behavior. We already saw this in few minutes ago. And this is a Bode plot, so this is the plot of this absolute value when we multiply by 20 and we compute the logarithmic by 10 of this function, okay? So this is the Bode plot, and this is, on this axis you have decibels. You can just represent this absolute value without using the decibels. It doesn't change much. The shape is more or less the same, okay? So this is just because this is a body plot, and that's why we are computing the logarithmic base 10 and then multiplies by 10 to obtain the decibel value. And also on the x-axis, instead of plotting omega, we plot omega divided omega s, where omega s is the sampling frequency, because in this way we get that these zeros happen when we are at multiples of 10. So this is in case this is 1, this is 2, 3, 4, 5, and so on. Okay, so just to make the a nice graph. So this is the shape that we obtain, and this is the sinc function. And what this means, if we look at the board, this is the representation of the absolute value of H0 of j omega. And if we overlap this with the ideal filter, then the ideal filter will actually have this type of shape. Okay? So you see that our hold device is actually approximating the ideal filter. It's trying to recover the squared value here and zeros here. Obviously, this is just an approximation, and there is distortion over here, distortion over here, there is distortion over here, and then there are also high-frequency values that are kept by the whole device. So if we look back at the slide, you can now understand what is the meaning of this. This is trying to preserve as much as possible the low values of the frequency, and then is trying to decrease the influence of high values of the frequency. Let's now look at the phase plot. So the phase of H0 of j omega, we say that is the sum of two terms, the phase of the sinusoid and then this term. So this term over here is just a term, a linear term that decreases to minus infinity. So when we plot it in semi-logarithmic scale, so in the body plot, what happens is that this becomes a curve that goes to minus infinity. And then we notice that there are these jumps over here. These jumps are actually caused by the phase of the sine. As we said, the phase of the sine, depending on the value of the frequency, is 0 or is plus or minus pi. So what happens is that when that 0 becomes plus or minus pi, we have a jump, and then that sign change again, and so we go back to 0, and then plus pi, and then 0, and so on. Okay? You can sketch a similar graph instead of summing pi, subtracting pi. In the end, this doesn't change much because obviously everything is normalized between minus pi and plus pi, or between 0 and 2 pi, or whatever band you prefer. This phase is a phase that is different from the phase that you are used to see in control systems, because usually in control systems you see phases that are actually bounded between, for instance, 0 and 2 pi, or minus pi and pi. In this case, instead, this phase goes to minus infinity. And you are also used to see in control systems that you are used to think that negative phases are actually bad because they decrease the phase margin, and so they are bad for stability. This is the case for the old device, and in fact, the whole device goes to damage the stability. So the fact that we have a whole device, a zero-hole device in the loop, actually creates problems. So why this problem is created? Well, the phase is actually associated with another time domain concept, that is the delay in our process. So let's see if we can interpret this as just a delay. And in fact, let's look at what happens when omega capital T divided by 2 is very small. So we are analyzing now this function when the argument is very small. So we have this function over here. We write it in this way. So we factorize again e power minus j omega t divided by 2, and we obtain this expression. Then when we write this for little values of the argument, what happens is that here we get 1 minus 1 simplify, and then we have j omega t over 2 minus j omega t over 2, so they sum. So we have basically plus j omega t, and this simplifies with j omega, so we have basically t. and then this term over here. So we get this expression here. This can also be seen over here, okay? So here we have the sinusoid. If we compute the Taylor expansion of the sinusoid, this is equal to omega t over 2 plus terms of higher order that we discard, and so omega t over 2 simplifies with omega t over 2, and we get this expression, t times this exponential, that is exactly the same that we have here, okay? So what is an exponential in the Fourier domain or slash the Laplace domain? An exponential, a complex exponential, is a shift in time, so it's a delay. So this means basically that at low frequencies, even at low frequencies, so when the behavior of the hold is as good as possible, we see that we have a delay of t over 2 seconds. So in our loop, the fact that we have an hold device introduces a delay. This obviously goes to damage the stability, because when we are controlling our system, since there is a delay of t over 2, it means that the information that we are processing is not actually the real information, it's a delayed information. It's what happened to the system t over 2 seconds before. So it means that we are trying to control something that does not exist anymore. It existed at t over 2 seconds before, and now the value of the signal is a different value. So you see that these create problems. Let's look now at the first order hold. So the first order hold is obviously more complicated, but has a very similar behavior. So let's look back at the transfer function. So the transfer function of the first order hold is given here. Okay, and the corresponding impulse response of this transfer function is given here. So now what we are going to do is to demonstrate this transfer function over here. So one way to do it, and you can do it as exercise, is to take this impulse response and compute the Laplace transform of this impulse response, and you will get this Laplace with this transfer function. We will do it in a different way. That is a more complicated way if you want, but it also makes you think in a different way than what you are used to. Let's look at the board. So here we have the first order hold, and what we want to find is its transfer function. So how do we do this? The idea is the following. We take the first order hold, we want to provide a certain input, and we know how the first order hold behaves and produce the output. So the output of the first order hold will depend on this approximation of the Taylor expansion of the value, as we have just defined a few minutes ago. So the idea is the following. Given the first order hold, given the input, we know how to write the output. Then we know that this scheme is actually equivalent to this scheme here, where we have the transfer function of u, so the Laplace transform of u of t, then we have the starred Laplace transform, then we have the transfer function of the whole device, and the Laplace transform of the y. So if we have the y of t, if we have u of t, we can compute y of s and u star of s, and then the transfer function of the hold is the ratio between y of s and u star of s. So let's pick an input, and the input that we pick is the most simple, so the simplest possible input, that is the unit step. And so we sketch here the unit step, a function that is 0 for negative values of time and 1 constant after. Then how the output behaves. So the output will be 0 for negative values of time because the input is 0. And then what happened here is that if we're going to replace the values, then when we are at this point here, so t is equal to 0, k is equal to 0. So here we have u of 0, okay, u of 0 is 1. And then here we have u of 0 minus u of minus 1, okay, because minus t actually, okay, divided by t. So when we are at this point, this term here, let's use a color, okay, this term here, okay, will be actually equal to 1 over t, if I'm correct, because this will be 1, yes, and this will be 0. So this will be 1 over t. And now we are multiplying this other term, but t is 0, k is 0, so this is 0. So at u of 0, this value will be 1. What happened, though, at this point here? So when we are reaching, just before reaching capital T. Well, let's assume that is capital T, so k is equal to 1. So we have u of t, okay, that is actually 1. And then this will be the same, 1 over t. And here we are in this amount of time here, so before capital T. So t will be t, okay, so the value of t that you are actually in. And then k is still 0, so this means that this will behave like t. So what we wrote here is that this function is actually equal to 1 plus t divided by capital T when t belongs to 0 capital T, okay? So when we are in 0, 0 included, to capital T is not included, then this function behaves like this. And so this means that it goes from 1 to, when this is capital T, this becomes 1, so 1 plus 1, 2. And so we end up over here, okay? Then what happens is that we have to compute the value of the function at this point, and what we will have is that it will be the value of the function u at that point, at capital T, that is 1, but then the slope will become 0 because you will compute the slope over here, and obviously the slope here is flat, and so this means that after we have 1, and it will be 1 after all, okay? So that's actually the behavior of that output. Let's now write y of t. So y of t is equal to, we say that from here to here, it behaves like 1 plus t over capital T. But this happens just when it doesn't happen for negative values, for instance. So this happens only for positive values of t. So we have to multiply for h of t. We remember that h of t is the step, the unit step, okay? So we indicate the unit step with h of t, or we can indicate it also with 1 of t. Sometimes I use one notation, sometimes I use the other notation. So let's use the notation y of t, so that is, 1 of t, that is less confusing, okay? So this function, again, is the unit step, okay? So this is 0, okay? But obviously we have to add something, because if that's the case, that's describe the function that continues in this way. So we have to eliminate this slope, and we have to end up over here. So we have to eliminate t over t, but when? We have to eliminate t over t when we are at this point and going forward. So we have to multiply for the unit step shifted by t. So you see that this function over here, okay, behaves between 0 and capital T like this. And then from capital T on, it behaves like 1 plus t over t minus t over t, so it behaves like 1. So we have written the function. So let's now do some computation. So this can be rewritten as 1 plus t over capital T, 1 of t. And now, since the end goal is to compute the Laplace transform, I want that the argument of the function in here matches the argument of the function there. So why? Well, this is, again, something that if you don't remember, and if you are if you don't understand this, maybe you should go and look at your notes about the Laplace transform. And it's a detail, so you may have to look very carefully. So here you want to compute the Laplace transform of that function. To do so, we first have to match this argument with the argument of the unit step. So to do so, we write as minus t minus capital T divided t, 1 t minus t. So we have modified this, adding a certain value, and we have to subtract this certain value. So you see that if you do this function minus this function, you actually end up getting that. Now we can compute the Laplace transform of y of t, Okay, so the Laplace transform of that is the Laplace transform of this term, that is 1 over s plus 1 over ts square. And then is the Laplace transform of this term over here. So the Laplace transform of this term over here is the same Laplace transform of this term, okay, but delayed of one sampling time. So the reason why we want to put the same argument is so that we can consider this as the delayed version of this function, for which we know the Laplace transform. So this is minus 1 over ts square e power minus s capital T. And then we have this, and this is the delayed version of the constant, and so it's minus 1 over s e power minus s capital T. Okay? So we can write this factorizing things. So you see that this term appears both here and here. So we can actually write this as 1 over s plus 1 over ts square, then multiplies 1 minus e power minus s capital T. Okay? So we have obtained this expression over here. Let's do an additional step, and in the last step we sum these two terms, and so we get 1 minus e power minus s capital T times ts plus 1 divided ts square. Okay? Okay, so that is the value of y of s. Now we want to write also u star of s. U star of s is by definition the sum with k that goes from 0 to infinity of 1kt, so of the sampled version of the function, okay, times e power minus k ts. So this is the definition of the starred version of the Laplace transform. And we know that this is actually equal to, we can interpret this, if you want, as a z transform. We already said that, as a z transform in which z is equal to e power ts. So we know that this sum is actually equal to 1 over 1 minus e power minus ts. Okay? Okay, now h1 of s is equal to y of s divided u star of s. So you replace this term and this term in there, and what we obtain is actually the value that the function that we have on the slide. So this is obviously seems a quite complicated way to obtain that transfer function, but is one way to obtain that transfer function. And now, as an exercise, you can use the other, more simple way to obtain the transfer function, that is to use the Laplace transform of the impulse response that is given here. So now we do the same study that we have done before on the zero order old. So we get the frequency response of h1, replacing j omega instead of s. We get the expression. Then we play a similar trick that we played before, and we get actually this function over here. Now we want to compute the absolute value and the phase of this function to see how they behave. So for the absolute value, we see that the absolute value of this function, again, the exponential here doesn't play any role. Then the t can be brought outside. Then we have the absolute value of the square of this function that is over here, and the absolute value of this function here. So this is a complex number, okay? It's 1 plus j omega capital T. The absolute value of this is defined as the square root of the square of the real part plus the square of the imaginary part. So this is the absolute value of h1 of j omega. If we represent this in the body plot, then we see that the behavior is actually similar to the one of the zero order old. So if we look back, you see that the behavior is similar. The difference is that this behavior is a bit more similar to the squared ideal filter. You see that this goes down later with respect to this. So this is a better version of the approximation. Let's now look at the phase and see what happened. So if we look at the phase, we have to compute the phase of H1, and let's do it at the board. So the phase of H1 of j omega is equal to the phase of capital T. Capital T is a real number, so the phase is 0. Then we have the phase of this term. So we said that when we compute the phase of the product of function, that is equal to the sum. So it means that if we have the power, then that becomes a multiplication by 2, because this is this function times this function, so it becomes the phase of this function plus the phase of this function. So we have 2 times the phase of sine of omega capital T divided by 2, right? Yeah. Then we have minus omega t, the phase of omega t capital T over 2. Then we have plus the phase of 1 plus omega, so j omega capital T. And then plus we have the phase of the exponential, so is the phase of e power minus j omega capital T. Okay? So let's go on. So this phase is 0 because it's a real number. So we have 2 times the phase of sine omega t over 2. And then we have the phase of this term. So this is a complex function, a complex number. And the phase of that is defined as the arc tangent. So the inverse function of the tangent of the real part, sorry, the imaginary part divided the real part. So it's omega t over 1. Okay. That's the definition of phase for complex numbers, minus omega t. Okay, so this is the phase and the expression that you get in the slide here. If we represent this, the behavior of this phase is similar to the phase of the zero order old. The difference is that this slope is going to minus infinity much faster. So if we compare it, so we see that when the frequency, the normalized frequency is 10, the value is around minus 30. In this other case, for the first order old, when we are at the same frequency, the value is around minus 60. So we see that this old is actually going to minus infinity 2 times as fast as the zero order old. And we said that this is bad for stability. Why is it bad for stability? Because this is linked to the delay. So let's go now to study what happened for low values of the argument. So for low values of omega capital T divided by 2, if we do the same approximation that we did before of this function, we get actually capital T times e power minus j omega capital T. The difference with before is that the argument is j omega capital T instead of j omega T divided by 2. So you see here that we have capital T divided by 2. So this means that now the delay is actually a delay of t seconds. So now instead of having a delay of t over 2 seconds, we have the double of the amount of the delay. And this is going to disrupt much more stability with respect to the zero order old. So the consequence of this discussion is that it's true that the first order old provides a better approximation of the signal with respect to the zero order old. However, using the first order old has 2 bad effects. One effect is that, as you saw, the analysis becomes more complicated. And the second very bad effect is the fact that the stability is damaged. It's damaged by the fact that the first order old introduced a delay that is larger than the delay of the zero order old. And obviously, if we're going to study higher order olds, like the second order old and so on, this delay will increase. And this basically implies that for control purposes, probably the best choice is to use a zero order old. I want to conclude this part of the lecture giving you a formula that is very useful in exercises and then is useful in the exam. So the problem is we want to compute the Z transform of a signal x of s, where x of s is given by the interconnection of a certain function that for now we don't know, and a zero-order hold. And we want to see what happened. So x of s is described by this expression here, where this is the transfer function of the zero-order hold, and this is the Laplace transform of g that for now we don't know. Okay? So how do we do this? So first of all, I want to make clear that the z transform of this, with this notation, I mean that I want to compute the z transform of the inverse Laplace transform of x of s, okay, just to make it clear, okay? But can we do this without actually, you know, trying to do it in an automatic way without doing too much computation? So let's define g1 of s as g of s divided by s. Then what we have is that the z transform of x of s is equal to the z transform of we multiply this by this term, so it's g of s divided s, so it's g1 of s, and then we have minus, and this is again g1 of s multiplying this exponential, so it's g1 of s e power minus st. Okay, so now to do that z transform, we want to compute the inverse Laplace transform of that. So that will be g1 of t, and that is minus, since we are multiplying for the exponential in the Laplace domain, this means shifting in the time domain. So this is minus g1 of t minus capital T. So now we can apply the z transform on this function, and using linearity and the shifting theorem, we know that this will be equal to g1 of z, so the z transform of this function, minus z power minus 1, the z transform g1 of z. Okay? So we can write this in a compact way as 1 minus z power minus 1, the g1 of z. Okay? So this means that if we want to compute the z transform of 1 minus c power minus s capital T s g of s, we have shown that this is actually equal to 1 minus z power minus 1, the z transform of g of s divided s. Okay? So this relation obviously holds for any g of s. So it's a formula that you can actually use in exercises. So when you have to compute the z transform of an interconnection of this type, this is always equal to 1 minus z power minus 1, the z transform of just g of s divided by s. So without doing all this computation again, you can use directly this formula. Obviously, for the first order hold, a very similar formula can be demonstrated. So let's do it. Let's give it, okay, then if you want you can prove it yourself. So the z transform of the first order hold interconnected with a g of s, okay, is equal to 1 minus z power minus 1 squared, the z transform of ts plus 1 divided s squared capital T times g of s. Okay? So this comes very easily because if we look at the transfer function, we see that this is this term, that is 1 plus ts divided ts squared times the square of this exponential. Now the square of this is 1 minus c power minus st becomes basically 1 minus z power minus 2. Okay?